Hello, everybody. I'm here with the topic of stress transformation, and this video is intended for both of my students. So let me write this down: stress transformation. And as I said, this is intended for both of my students at Northeastern. The Northeastern students will see this lecture earlier, and my Wentworth student will see it in a couple of weeks. So I've already done a video on. Sorry, I had to pause the video for a second. I had a phone call. These are hectic days, with email, phone calls, emergency things. Anyways, let's get back to the business. So here what I have, in general, I wanted to show you a three-dimensional stress element. So what is this stress element? This stress element is a point on a structure that, could be a critical point, and you can calculate stresses due to different things. Normal stresses due to axial load or bending, and they could be combined, and they could be in X and Y direction, as you could see here, and then also in the Z direction, and then shear stress tau X, Y. So by the way, I just showed you, I didn't want to crowd this picture here, but you could have a shear stress in any direction. And I want to talk first about the sign convention and also these subscript. So for example, tau XY, what does that mean? The first subscript actually is the side or the plane, and the second subscript is what? Is the direction actually. So you see this tau XY here, it's if you look at the center of this cube as your reference, we are on the X plane or X side, so we are on the X side and we are acting in the Y direction. So this one over here, we called it tau YX because we are on the Y side and we are acting in the X direction. Also, in terms of the sign convention, if the side is positive and the direction is positive, then positive times positive becomes positive. So this shear stress acting up like this is a positive shear stress, as well as all these other shear stresses that I've shown here. So you guys remember that shear stress, once you have it on one face, it must be equal on all the other faces, right? Because otherwise there would be, you are not satisfying the equilibrium, and it could rotate. The element will rotate. Also, let me show you one more, even though it's not really important. For example, what would be stress like this? This one would be tau sub Y, because we are on the Y side. Remember, the first one is the plane. And in what direction this guy is acting? This guy is acting in Z direction. So it would be tau YZ. And then remember, there would be one like that, one behind it going down, and one on this plane going the other way. Now, obviously, this is going to get too messy. I could show you all the shear stresses, but this situation really doesn't happen in a given problem. The most you could have is something like this that I've shown you here. Now, we want to concentrate on a two-dimensional element, a stress element. We don't need to look at a three-dimensional element like this. A two-dimensional element is called as a plane stress. Whenever you set all the Z components of stresses, like sigma Z equals 0, tau XZ equals 0, and tau YZ equals 0, then you will get what we call a plane stress. So then you're dealing with the stress element here. By the way, one thing I forgot to mention, and I mentioned it kind of indirectly here, is that tau XY must be equal to tau YX, as shown here. So this guy is the same as this guy, right? Because otherwise the system would not be in equilibrium. All right, I hope this is not getting too messy. But in any case, so now we want to concentrate on a stress element like this, a two-dimensional version, a much less complicated state of stress, which is known as what? As plane stress. Okay, So now what's the next, what is a stress transformation then? Stress transformation means that if you have this element in the XY plane the way it's shown, what happens if you look at some other plane like this, okay? So what happens to the stresses? So if you kind of, in a way, rotate your axis. Remember, there is no rotation involved. I'm just talking using the word rotate here. So x prime axis and y prime axis. By the way, in for my students at Northeastern, in the textbook, x prime is n normal and y prime is t tangential. But I wanted to be efficient and make this video for both courses at Northeastern and Wentworth. So x prime y prime is what we're using in the Hibbler book. And the PowerPoint presentation that I showed you guys, actually, I did mention that they're using x prime, y prime, because the PowerPoint presentation is from Hibbler. Okay, anyways, so the question is, how do you do this? By the way, what we did here, we actually came here and we cut this at some angle theta. So this becomes basically our y prime axis, and this becomes the x prime axis that you see here. Exactly what you see here, x prime and y prime. Okay, so if you now look at this element, right, in order to get a free body diagram, you see over here we have on this triangle here, this green, what stresses are acting. We have a sigma x here, we have a tau xy here, we have a sigma y, we have a tau xy there, but they are stresses. They are not forces. We have to change them to forces. How could we change them to forces? We have to multiply them by the area over which they are acting. So we said that if this area here, which is really something like this that you see here, is dA, some differential area or a small area, or delta A. Actually, I call it delta A. Then, based on this angle theta here, this would be what? Delta A cosine theta, and this would be delta A sine theta. Therefore, if you take this sigma x, for example, and multiply it by delta A cosine theta, it becomes the force here. And similarly, this tau xy here is acting on this plane here. So you multiply it by the same area. And similarly, you do the same thing. Interestingly enough, I forgot to put my sigma y here. Good thing I just saw it. Times delta A sine theta. So here, now you have the free body diagram, and also delta x, sigma x prime has to be multiplied by delta A, and tau x prime y prime has to be multiplied by delta A also to make it what? Stress. Because remember, this is acting on what? I guess I paused it, the video again by mistake, guys. Sorry. So I'm not going to show you all the detail of it, but now what's the objective? Our objective is to find stresses along this plane, both normal and shear stress. So our objective is to find sigma x prime and tau x prime y prime as a function of angle theta. So let's go to the next page. So all you have to do, guys, is sum forces along the x prime axis, set it equal to 0. And after doing some, setting all the forces in the x prime and y prime equals 0, you come across this equation. Of course, the equation is going to be in theta angle. But why is all of a sudden our equation is changed to what? To theta. We can use some trig identities to go from theta angle to 2 theta angle. And the reason we do that is because it's more convenient later on when we want to talk about a graphical approach known as Mohr circle. So we'll talk about that later on. And then when you set sum of the forces in y equals 0, that will give you this equation. And then there is also an equation for sigma y prime. So you see that this is the initial element, right, that you have. Now look at the element at a different plane. So theta angle, by the way, positive theta means counterclockwise plane, rotation, or, looking at the plane counterclockwise to your initial plane. Anyways, so take a look at the equations here, sigma x prime and tau x prime y prime. And then the question is, what about sigma y prime? Sigma y prime actually is this plane. So basically, if you add to your theta angle, another 90 degrees, you get to that plane. So theta plus 90, when you double that, it becomes 2 theta plus 180. And you guys know that sine of, for example, 2 theta. So basically, in this equation, if instead of 2 theta, you change it to 2 theta plus 180, right? What is sine of that? It becomes minus sine 2 theta. And similarly, cosine of 2 theta plus 180, all right, if you add 180 to an angle, it becomes minus cosine 2 theta. So notice that the only change between sigma x prime equation and sigma y prime equation is that this positive becomes negative and this one also becomes negative. Good thing I'm catching all these errors here. Okay, so one other thing, by the way, I can show you is that one interesting thing is that if you add sigma x prime to sigma y prime, that should be the same as sigma x plus sigma y. And I will show you shortly an example in a video, right? And this equation is very useful because this equation tells you that the sum of two normal stresses in two perpendicular planes. So let's say sigma x and sigma y are what? 90 degrees apart, right? That sum is the same as what? The two normal stresses on, again, sigma x prime and sigma y prime. On the plane of the two perpendicular planes. Okay, so this is going to be true. So the good thing about this equation is if you happen to know your sigma x prime, you really don't have to use the formula for sigma y prime. So these are the transformation equations, guys, that we were talking about. And later on, we'll come back and talk about how do we look for maximum of these. How could I find the maximum of sigma x prime, a maximum of the tau x prime, y prime? And those are important in design. And those are known as, the normal stresses are known as principal stresses. And also maximum shear stress is very important in design. So I hope that I didn't confuse you guys. You can always go through this and keep watching it. And later on, I'll have virtual office hour and try to answer your questions. As always, thanks for watching and listening.